Okay, so welcome back to room 304 with, as you may have noticed, the usual technological problems. I've got most of the board in the camera, so I'm going to try and write on little bits of the board. And if we decide to do anything secret from people watching, then we'll use the margins of the board. Anyway, it's just for this week. So what we're going to do today is we're going to talk about proof systems. And I think the notion of proof system is one of the most important things that logic contributes to mathematics. So we already discussed in the second lecture, when we had the first two lectures were introductory lectures, and the second lecture in particular, I talked about axiomatizations and how very importantly in logic, we have a notion of what it means to be able to correctly prove that a statement is a consequence of some axioms. And mathematically, the way that works is we have a notion of a proof system, and the proof system gives us the precise rules we can use for deducing consequences of a set of axioms. And it's very nice that we have such proof systems that are relatively easy to write down and enjoy a very important property, which we'll see later today, that they are complete, where completeness here means that if it's true that some statement is a logical consequence of a set of axioms that we have, then the proof system is complete in that there will exist some way that we can prove that consequence using the rules using the rules that we have in our proof system. So there are very many proof systems that exist in mathematical logic, and they have their pluses and their minuses. Broadly speaking, they divide into two groups. Other people might classify them differently, but I would say they have proof systems that support what one might call natural styles of proof, where a natural style of proof is the kind of proof that is natural for us as humans to reason with. So if you have such a proof system, it's quite useful, because if you have an informal way of proving something, you've kind of worked out the argument for yourself, and you write down the proof in the natural style that you have for reasoning, it actually turns out to be not too difficult to translate that proof into a formal proof, because the formal proof in this kind of system sufficiently closely follows a natural style. And there are two particular such styles of proof. One is actually called natural deduction, because it formalizes natural reasoning. And another one is called sequent calculus. Now, probably many logicians would take issue with me putting this in under proof systems that support natural styles of proof, but sequent calculus is not really that far from natural deduction in many respects. It's very easy to convert between, well, relatively easy to convert between one and the other. And actually, proof assistants, computer proof assistants that are implemented, well, they tend to work on something called type theory, and they tend to support a natural deduction style of reasoning, but many of them also support rules along the sequent calculus style. So I think these fit naturally together in a package. And a big advantage of these systems is they're easy to use. These kind of proof systems are easy to find proofs. It might not be easy to find a proof because you might be proving something that's very hard to find a proof for, but if you have a proof, it's tends to be easy to transliterate it into the proof system. So that's just saying, anyway, easy to write proofs. So then we have the other style of proof system. Let's separate. We've got a nesting of lists here. So these are bullet points and these are dashed. So the opposite style of proof system, well, proof systems that support unnatural styles of proof. Now let's call it contrived styles of proof. The most famous of these is the kind of proof system that we're going to look at today, and that's it's called the Hilbert proof system. There are many of them, so there are many in this style, but they tend to support contrived styles of proof. Maybe one other that's important to mention here is something called resolution, which is a very contrived style of proof, which was designed to be useful in automatic theorem proving. The idea here is that all inference is reduced to just one rule of inference. There's only one rule that works, and the computer just basically, so it helps with computer search. If you're trying to find a proof for something, you search all possible ways of using this rule of inference, and hopefully you find a proof. And the first ever computer proofs, automatically found computer proofs of open mathematical problems, were found using this method, by a theorem prover called Ocker in the 1990s. Some proof that, I think the first one was some proof that every Robbins algebra is a Boolean algebra, or something like that. Yes, did you have a question, Gregor?
Would analytic tableau go under the...
Aha, analytic tableau would go under the natural style of proof system. There's something called tableau, and they're also kind of intertranslatable with secret calculus in a way. Okay, so here there's a negative, which is not easy to write proofs. Let's maybe change that to find or give. Anyway, not easy to give proofs. So the reds are negatives. This is a plus. Not easy to give proofs. I'm not going to write everything down. So with resolution, the plus was that it's only one rule of inference, so it's easy to automate. There's a different plus I want to emphasize for this style of proof system. Let's first go to a negative for these natural styles of proof system. And the negative is they're a little bit complicated. It's a little bit complicated to formulate exactly what the rules are and to precisely say how to follow them. And that's going to be important in our course because one thing we want to, our main goal of our course is to get to Gödel's incompleteness theorems. And the proofs of Gödel's incompleteness theorems require us to have very precise and formal definitions. Well, all these notions of proof give precise and formal definitions, but we're going to have to encode a proof system in arithmetic, which is the first order theory of the natural numbers. And the simpler your rules are for your proof system, the easier it is to encode it into arithmetic. And these turn out to be a little bit complicated. So it's not so easy to formalize. That's the negative here. And the benefit that is really going to pay dividends for us, so let's make it a double plus because this is the decisive factor for why I'm choosing this proof system for this lecture, is that it's going to be relatively easy to formalize. I mean, let's just say easy to formalize. That's something we'll come to later in the course, the formalization aspect. Today, we're just going to understand the proof system itself. So we're going to deal with Hilbert systems. I'll give you example of the Hilbert system we're going to use in a moment, and then we're basically going to spend today studying it and understand why it's complete. That's the main goal today, to understand the completeness property that I mentioned earlier. But before going on to it, I just want to say a few more words about these natural styles of proof system, because my preference is very much for these natural styles of proof system. They're the ones that are useful in proof assistance. And also they turn out to be useful for some meta-mathematical purposes in logic too. So remarkably, both these styles, it's two different styles, but they're closely related to each other. But both these styles have been very, very influential in logic and also outside it, for example, in formal proof assistance and in philosophy and in other areas. Remarkably, both these styles were introduced in the same paper by Gerhard Gensen in 1936. So a single research paper, he introduced both styles, and then he went on to he preferred sequent calculus for various reasons, and he went on to use it for some to get some rather powerful results, one of which was to give a proof of the consistency of piano arithmetic. That's all very interesting work, and it's very natural to look at that in the context of having already seen Gödel's incompleteness theorems, which we're going to do much later in the course. And because sequent calculus is important, we are going to cover it in this course, but this is going to be lecture 14 and lecture 15 of the course. So these are going to be the last two lectures of the course. So this is something to look forward to. So I don't know, now we're on lecture 6 or something like that. I'm not completely sure. Okay, so we'll come back to the natural styles of proof systems, the natural style of proof systems. But now we're going to look at a contrived style of proof system, in particular, the Hilbert system. So as I said, for us, the decisive benefit of the Hilbert systems is they're going to be easy to formalize. And to make things easy to formalize, we want to make everything as simple as we possibly can. So the first thing we're going to do is simplify our logical language. The first step, simplify the logical language. It's not necessary to do this, but we want to make everything as easy to formalize later on when we come to doing the formalization in arithmetic, as easy to formalize as possible. But also another reason for doing this, it's kind of fun to do it, to try and make everything as simple and as concise as possible. So essentially what we're doing is we're applying what's called, I don't know if you have this phrase in Slovene, but in English it's called Occam's razor, the principle of parsimony, trying to make everything as simple as possible. In the case of coming up with a proof system, we want the minimum language, as few axioms as possible, and as few rules of inference as possible. So I'm going to give what I think is the simplest system. If you have an improvement to it, I would love to hear it. And so an improvement meaning an even simpler version would be great. So we're going to simplify the logical language by, we're only going to consider, false, implication, and the universal quantifier. In most textbooks where the textbook writer is similarly minded to me and likes to try and make things as simple as possible, they use negation, implication, and the universal quantifier. We don't need negation because we can define negation. Obviously, not A is now henceforth going to be an abbreviation. So in today's lecture, negation of A is just an abbreviation for A implies false. And we can similarly define the other connectives. For example, once we've defined negation, then A or B is simply an abbreviation for not A implies B, and you can work out conjunction for yourself. Existential quantification is not for all not, so we can do that. So anyway, we already know from many lectures ago that this is a sufficient set of connectives and quantifiers. The reason I like to have false is because it's very useful for, we're going to use false for a few purposes today. One can always define false as, for example, for all x, it's not the case that x equals x. That would be a definition of false. But, you know, it's such a simple concept. I like to have false as a primitive concept. Yes, Gregor, again?
You could replace these two with a chef stroke, I think.
Oh, well, okay. So there is this nice fact in logic that there are two binary connectives that either of them can be used as just a single connective. One is called the Sheffer stroke. I think that's NAND, not and the other one is not or. Actually, I don't remember which one is the Sheffer stroke. So we could do that. So then we will make this a little bit shorter, but I'm not sure. So I'd be very interested if you can give me a very simple set of axioms for the Sheffer stroke.
Yeah, I see.
So but maybe you can,
Maybe.
because here we've got the language. The next thing we do is we look at, so we've got our language, and now we're going to consider a list of axioms and inference rules. So the proof system, we have some proof rules, those are called inference rules. We have some logical axioms, those logical statements that are valid that we can start off with in our proofs. So let's do that on the other board. You probably can do that simply for the Sheffer stroke. There are other reasons for using universal quantification and implication. So they are natural. They are very natural operations. That's one basic operation that one reasons with. And the axioms are going to have a connection to type theory that I'm going to mention, where it's crucial that we're using implication as the connective in order to get that connection, because it connects with the function space in type theory. So our axioms, there are going to be a finite number of what we call axiom schemas. So a schema is a single axiom pattern that we can, that any instantiation of it using actual formulas counts as an axiom. So the axiom schemas, I need to remind myself. There's a second pluralization of schemas in English, which is schemata, but to me it sounds very pretentious, so I shall use axiom schemas. We simply have 7 axioms. First one is A implies B implies A. As I say, this is a schema, so A and B are meta variables standing for formulas, and any instantiation of this axiom with this schema with a formula for A and a formula for B, we allow formulas, not just sentences. So in the literature, you do occasionally find proof systems that only work with sentences. So there's a nice book by Foundations of Maths books that you lent me, in fact. Who's it?
Kenneth Kuhn.
By Kenneth Kuhn. He has in that a proof system that only involves reasoning with sentences. That's actually quite non-standard. It's helpful to reason with formulas. So for us, these are meta variables standing formulas that may have free variables, not just sentences. Of course, there's an implicit bracketing here. Hopefully you all know that implication bracket associates to the right, so that's the bracketing. We're going to fit 7 axioms here, I think so. So the second one is, I'm now going to leave the bracketing to you. So A implies B implies C, implies A implies B, implies A implies C. Third one involves negation, which is, of course, an abbreviation. So although we're putting false in, the axioms naturally talk about negation rather than rather than false, but still, I like to have negation defined using false. So this is the law of contrapositive. Let's see which way I've got it. Yeah, not so. If not B implies not A holds, well then this is the axiom that we build that builds in classical logic here. This is not an intuitionistic, for those of you who know something about intuitionistic or constructive logic, this is not a constructively valid principle. There is the converse implication to this is constructively valid. Just to make sure we've got enough space. The fourth and fifth axioms involve universal quantification. So if for all xa holds, here we're bracketing that, then maybe I should make that clear. Then A holds for any term t replaced x. So that's very intuitive. If something holds universally, then any instance of it holds. Sort of distributivity property. I don't know if that's the right word actually, but you've got an implication holding universally for A and universally for X, and X does not occur in A, then we can pull A out. So A implies for all XB. So the condition here is if X is not in the free variables of A. And finally, two axioms involving equality. We need to specify what equality means. So the first one simply says that any term is equal to itself. And the third one, sorry, not the third one, the second one about equality is a schema that says that that equality has the property that we expect of it. If two things are equal, then any property of one is also a property of the other. So we can say that by saying that in any formula, A, if A holds where we substitute t for some variable z, then A also holds if we substitute u for the same variable z. Now this device, so here A could contain lots of free variables, but we're singling out one z and we're substituting t for it, and then we're substituting u for the same. Sorry if you can't see this stuff. Can it be seen on the computer? Yes. So yeah, then we're substituting u for the same occurrence. This device is very useful. It's a way of saying if a property A holds for t, then the property A holds for u. And so henceforth, I'm going to, when we do this, we're replacing the same free variable with two different terms. I'm going to use this square bracket notation and not explicitly say what the name of the variable we're substituting in, because it doesn't really matter. This is A with some distinguished, we can view this as a formula A with some distinguished occurrences of the term t. And then here we have A with where t was, we're replacing it, that term with u. Okay, so these are all the axioms. So this, for those of you who know something about lambda calculus and combinatory logic, which may not be very many of you, but just for those who want to hear the connections, the nice thing about choosing the implication here is these first two axioms, which are sufficient for the implicational fragment of intuitionistic logic, these two axioms, they don't axiomatize all even purely implicational statements in classical logic. A fun exercise is to find a purely implicational classical statement that does not follow from these two axioms. But these can be considered as types in combinatory logic for the main combinators in combinatory logic that relates to lambda calculus. This is called the type of the K combinator. This is called the type of the S combinator. So just for those of you who want that connection to be made. So these are all the axiom schemas. We then have just two rules of inference. So actually, let's put the rules of inference on the board here. So the way a proof is going to proceed is a proof is just going to be a sequence of formulas, where each formula in the proof is either an instance of one of these axiom schemas, or it's obtained from previous formulas in the proof using a rule of inference, or it's something we called an assumption, where we call an assumption, where an assumption will be some, these are the logical axioms, they're all logically valid. An assumption will be some non-logical axiom which we might take from the axiomatization of a theory. For example, the axioms for the theory of groups, or the axioms, Peano's axioms for arithmetic, or something like that. Anyway, I'll formalize the notion of proof a bit later. But the inference, so these are the axiom schemas, the inference rules, put them here. We just have two, and we write inference rules like this. We write a line, and above the line we put something called premises. And once again, these are going to be schematic. So here the premises, which way? Let me just put it the same way around. I've got in my notes, doesn't really matter. So the premises are, if we already have this formula, an implication A implies B in the proof, somewhere in the proof, so we've already established A implies B, and we've established A, then unsurprisingly, it's okay for us to establish B. So we can add B as a new formula to the proof. Okay, does somebody know the Latin name of this rule of inference?
Modus ponens.
Modus ponens. So MP, modus ponens. That's the name of the. The same, this is a very natural rule of inference. It's so natural, it is also a rule of inference in natural deduction, an important rule of inference in natural deduction. In natural deduction, it's called implication elimination, because we're eliminating in natural deduction, every connective has both an elimination rule and an introduction rule, and this is the rule that eliminates an implication. We have an implication and we can get rid of it. The other rule we're going to have is that if we have a formula A, then in the proof, then we can put the formula for all xa in the proof, as long as there's a side condition here. So as long as, so condition, which is that the variable x does not occur free in any assumption in the proof. So I'll say what an assumption is. So
do we have assumptions like syntactically in Hilbert calculus?
we're going to allow ourselves to have assumptions, yes, in a moment. I mean, I call them assumptions. Other people might call them other things. The point is, we can think of this as x does not occur free in any of the formulas that we've assumed properties of earlier in the proof, and therefore, by the time we've established that A holds without there being any assumed properties of the variable x, and for that reason, A holds for a generic x, so to speak, and therefore we can establish that A holds for all x. So this is called generalization. Once again, this is a natural rule of inference. It's like saying, if we've established A holds for an arbitrary x, then that means we've established for all x. It's a very natural principle. It's how we typically reason about universal quantification And so once again, this rule occurs in natural deduction, where it is now called the introduction rule for the universal quantifier, because this time we're introducing the universal quantifier. Okay.
This should probably say does not occur.
Oh, you certainly should. Yeah, thank you very much. I think I said does not, at least I hope,
Yes.
at least I hope I did. Yes, it should definitely say it does not occur. So I'll be more precise about what's meant by an assumption in a moment. But before giving the precise way that we interpret these rules, let's give some examples of proofs. So I'm going to do two, and the reason for doing these examples is, well, so that you see what a proof looks like, but also so you get to appreciate a little bit the statement that I said earlier, that the proofs are contrived and not easy to find. So we'll begin by a proof of a particular formula, which states one of the basic logical properties of equality, that it's a symmetric relation. So we're going to prove, example proof of for all x for all y, x equals y implies y equals x. Okay. And for this kind of thing, the proofs are so unnatural, it's absolutely essential I have my notes with me. There's no way, there's no way I would be able to on the fly come up with this proof in a lecture in front of you. So we start with the implication x equals y implies x equals x implies y equals x. This is an instance of one of these axioms. Can anyone see which axiom it's an instance of?
7.
Aha, right. We have, it looks like it might be an instance of this, because it's similar, this looks the same as that, except it's not big. Syntactically, it's not. We have to deal with things syntactically because we swap the y and the x around. So actually, it's an instance of the seventh one, where now obviously t is x. So let's write the x. So this is axiom 7. So t, so x is t is x. Let's write an equivalent for this. Means t is the same thing as x, u is the same thing as y, and the formula a with the z in is, so a is then a is the formula z equals x. I think that works. So we've got z equals x replaced with t, which is x. So we get x equals x there. And then z equals x replaced with u, which is y, and we get y equals x. Okay. So that's an instance of axiom 7. Then we notice that we've got the following formula as an instance of another axiom. X equals y implies x equals x implies y equals x. The reason for, so we're going to carry on here. The reason for using this one is we've got the same formula as here, and we want to be able to use this formula to get rid of this using modus ponens. So that's why we kind of tried to build a formula out of this. And well, actually, let me tell you, this is going to be axiom 2. So once we've got, this is our A implies B implies C. So now we need A implies B. So x equals y implies x equals x equals x implies A implies C. So x equals y, we don't need this bracket, but it's there, implies C, which is y equals x. So that's axiom 2. And now we're going to apply modus ponens to these two. So this is an implication here, and we've derived the antecedent to the left side of the implication. So we get back x equals y implies x equals x, implies x equals y implies y equals x. So that's modus ponens on sorry, these are axioms 1 and 2. This is modus ponens on 2 and 1, meaning the statements we already have in the proof. We're going to run out of space. There's actually, so I need 9 steps. Well, we'll just wrap around when we get there. So statement 4 is now an instance of axiom 1. X equals X implies X equals Y implies X equals X. And then using axiom, so then statement 5, we're going to use axiom 6 and just use X equals X. So this is so this was axiom 1, axiom 6, and now we can use modus ponens on these two. So modus ponens on 4 and 5, and we get X equals Y implies X equals X. Now we've got X equals Y implies X equals X, which is the left-hand side of this implication. So modus ponens again gives us, we are going to be able to fit it on. So X equals Y implies Y equals X. Okay, so modus ponens of whatever it was, 4,
3, 6.
Thank you. Yes, modus ponens of 3 and 6. Okay, right. Maybe my explanation of what an assumption wasn't very clear before, but now we can see we're almost here. We just need to do 2 generalizations. So 8 is for all Y, X equals Y implies Y equals X, and 9 is for all. So this is generalization, and for all X, for all Y, X equals Y implies Y equals X. And we're done. So firstly, it's quite complicated. Here we're using generalization. So what does generalization mean? Well, it's that X does not occur free in anything we call an assumption. An assumption, I maybe said the wrong thing before. Now I remember what the correct definition is. An assumption is a logical formula we use in the proof that we say, okay, we're going to assume this and prove some consequences from it, that is not an instance of one of these logical axioms. So here we've got plenty of free occurrences of X and Y occurring above, but they're okay because they're instances of the logical. These are instances of logical axioms. We're going to allow in our proofs the possibility to put formulas in that we're just assuming. And we're going to do that because what we want with our proof system is to get a general notion of a consequence relation. The proof system is not just able to prove what is outright valid, but is also able to prove when one set of formulas, when one formula is a consequence of some other formulas. We could restrict assumptions to sentences. That would be okay for all applications. But for the sake of the completeness proof, it's really very useful to be able to know how we can derive formulas from assumptions that are not sentences. So for that purpose, we're going to allow ourselves to make assumptions that are just formulas, not sentences. Yes, Gregor again.
Yeah, but the calculus loses none of its expressivity if we don't allow the concept of an assumption, right? Because any with the turn style symbol in between any such statement can be just converted to an implication in the language, right? If I understand correctly.
So what's true from the calculus, the way I formulated it, what's true for the calculus that I formulated it is that in future we're going to apply it only to the assumptions will always be axioms from some theory that we axiomatize, like the theory of arithmetic, in which case they're always sentences, so we will only need assumptions that are sentences. However, the way I formulate things having assumptions that are formulas cannot be mimicked by having assumptions that are sentences. And for the particular style of completeness proof I'm going to do, that's going to be important. So assuming an assumption that's a sentence, that's a formula, is different from assuming the universally quantified version of that. But this is not the way everybody does it. It's the way I like to do it. Okay, it's nearly time for the break, but I want to, while we're doing proofs, let's just get them out of the way. So I want to fit in one more proof. I'm going to rub this one out. This is a proof of a particular sentence. Okay. Often one, because the axioms are schematic in this sense, often one can give schematic proofs where you're just using the schematic form of the axioms, and the schematic proof you can instantiate with any to any instantiation of the A and the B and so on to particular formulas. So let's now do the schematic proof of one of the simplest valid formulas schemas for valid formulas in logic, which is the schematic proof. So the schematic proof just means any instantiation of it to individual formulas will work. We're going to do a schematic proof of that A implies itself. Okay. And this is a bit shorter, but still it's more complicated than you would like for a proof of A implies A, which is a very basic property. So we start with A implies 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 A. Which axiom is this an instance of? Indeed, 2. So axiom 2. This is in axiom 2. This is A. This is B, and this is C. Okay. Well, that's the longest formula in the proof. So now, an instance of axiom 1 is this. But A implies A implies A implies A. We do modus ponens on these two, so modus ponens on 1 and 2, and we get that. So that's A implies A implies A implies A implies A. Again, by axiom 1, we get this left-hand side. A implies A implies A. So by modus ponens on 3 and 4, we finally get what we wanted. A implies A. And once again, this is it's a very simple logically valid formula, but this is the type for the combinator, the identity combinator I, for those of you interested in combinatory logic. So this is again this proof, you can encode it as the way of defining the identity combinator using the S and K combinators in combinatory logic and application. And in fact, it's encoding the famous identity I can be defined as SKK. I don't quite remember how that's bracketed, or if it's bracketed. I guess it's just that, but we can think about that in the interval. Okay, so proofs in Hilbert systems are great fun. It's very good that they're great fun because you're going to have a lot of fun next week in the exercise classes. Right, okay, so by the clock on the back wall, it's 5 o'clock, so we'll break until 5:15. Okay, so we've done 2 examples of proofs. The proof of the particular formula, the symmetry of equality, and the schematic proof that A implies A for any formula. We have A implies A. I just wanted to give you, if you like, a list of exercises. maybe you'll do some of these next week, but it's fun to establish properties by using the Hilbert proof system. And some of these properties we're going to actually need later today. So I wanted to just give a list of them. So these are all, let's call it schematic proofs. And these are all instances of similar formula schemas that can be proved by such schematic proofs similar to the one that I gave for A implies A. So first one, these are, think for yourself why this is valid. Here we're essentially swapping two antecedents of an implication around. You've got A implies B implies C there, and B implies A implies C there on the right. And I was including this one because for people who like combinators again, this is one of the famous combinators, the C combinator. Yet another combinator is the combinator that does composition. So if you have B implies C and A implies B, then we can kind of compose those implications and we get A implies C. This is called the B combinator. And then another important consequence of the axioms don't talk about false at all. That was a primitive symbol. But as a consequence of them, we do get that false implies anything. So this is, people sometimes puzzle about this implication when they first, does false really imply anything? A bit worrying in today's political situation if false implies anything, because there's plenty of false around. Anyway, but from our axioms, this is the consequence. So of course, here we've got going from an implication to its contrapositive in one direction. As we know, implications are equivalent to their contrapositives. So the other direction of that is also provable by an easy schematic proof. So A implies B implies not B implies not A. As I said, the third axiom gives us classical logic that can be emphasized by the law of double negation elimination. And then another property that I think is in the list because it's going to be useful is that if not A implies A, then A holds. Okay. So that's enough, I think, in the way of consequences of the axioms. So I've mentioned this notion of assumption, but we haven't actually seen any use of assumptions so far because everything I've been proving so far has been proving valid formulas. I want to keep the inference rule, the axioms and inference rules on the board a little bit longer. So just be careful with the taking cables, please. So we'll continue working on this board. So the reason for mentioning a notion of assumption is the following, that what we really want from the proof system is not just a means for proving outright that a formula is valid, but a mechanism more generally for deriving that one formula is a consequence of a set of other formulas. And then we can use that when we have an axiomatization, because we take our set of other formulas to be a given set of axioms, and we have a mechanism for proving that a formula follows as a consequence of a set of axioms. So this is captured by what we call the derivability relation, and we're going to, the derivability relation is defined using the proof system. So the point of the a major point of introducing the proof system is to be able to define a derivability relation. Derivability relation going to use a notation. We have gamma for a set of formulas. We use the turnstile A. This says A is derivable from the set of formulas gamma. So A is derivable from gamma. And this holds. We define. So this holds if there exists a proof with that's a finite sequence of formulas with conclusion A. So the proof, notion of proof is defined more formally in the LaTeX lecture notes. But it's a finite sequence of formulas where A, the conclusion, that's the last formula in the sequence, is A, in which every formula in the sequence is either an instance of one of these axiom schemas, or a formula in gamma, or obtained as the consequence of one of the inference rules from two formulas occurring from formulas occurring earlier in the proof. From two formulas in this case and from one in this case. And when a formula from gamma is used, we call that an assumption, with conclusion A, and in which all assumptions are taken from the set. So I've said that, I hope, clearly enough. I'm not going to actually write out all those things, a finite sequence of formulas with all those conditions. But I've defined what it means with words, and which all assumptions are taken from the set gamma. Okay. Now, importantly, gamma, and this is important for the results we're going to prove, gamma can be an infinite set of formulas. And this makes sense, this relation makes sense if gamma is an infinite set of formulas. Of course, in the proof itself of A from assumptions in gamma, only finitely many formulas in gamma will be used. But still, we write that A follows from the whole set of formulas. And when we write this, we don't know which finite set we're going to use. Okay, so in any individual proof, we only use finitely many assumptions, but the notion of provability makes sense for an infinite set here. Now, this is like the notion of logical entailment, which we defined in, I don't know, lecture 2, I think it was. Only it's defined using a proof system. And the very important results about the proof system are going to be what are called soundness and completeness, that together say that this relation is actually the same as the relation of logical entailment. But before we go to soundness and completeness, I want to mention two just syntactic properties that one can prove about the derivability relation purely from its definition using the proof system. The first is a very important little proposition called the deduction theorem. this says if we can derive B from a set of assumptions gamma together with the formula A, then without using A as an assumption, we can derive the implication from just the assumption B gamma, we can derive the implication A arrows B. So it's the implication A implies B. So this is a very important result because it basically, once we have this result, it shows that in our proof system we can mimic natural reasoning about implication. We already have the modus ponens rule, which is the natural elimination rule for implication. And this is like the usual introduction rule for implication. The usual way one introduces an implication into a proof is you assume the antecedent of the implication, you derive the conclusion of the implication from that assumption, and then you say, okay, because I managed to do that, A implies B whole. And this result, which is a theorem about the derivability relation as we defined it, this result says the same thing process is valid for the Hilbert system. Only in the Hilbert system, it's not one rule of inference that gives us this. Rather, it's if we have a proof like this, we can perform some process on it and convert it into some proof like this. Now, there's a rather nice proof of the, well, I mean, depends what one likes in the way of proofs, but it's not that hard to prove this result. This lecture's not that well written up in the LaTeX notes, but I have some handwritten notes that I'll put online. I don't really want to spend time in the lecture on the proof of this. So if you're interested in how to prove this, you can look in the handwritten notes online. There's one, at the moment, there's one little index J in the proof that should be an I, but I'll let you figure that out for yourself unless I have time to correct it. Anyway, so this proof will be in the handwritten notes online. One other thing to say about it is that the proof of this, I've been emphasizing connections with combinatory logic. For those who know about such things, the proof of the deduction theorem is essentially the proof of what's called combinatory completeness for the combinators that have the types that are the axioms in the axiom system. It's basically the same proof. So that's the first. That's the first real meta theorem about our notion of deduction, about our derivability relation. Although I do just have. I'm sorry for those of you for whom this is squashed at the bottom of the board, but given that the space is there, I do have space to put the other meta theorem in, which we'll call a proposition. And this is following holds, and it's actually a straightforward consequence of the deduction theorem. And again, the proof is in the notes, and I don't want to spend time in the lecture on the proof of this. But this says that it's again what happens about if we add a new assumption A to a set of assumptions. It turns out that if adding an assumption A, we can prove B, and also we can also prove B if we add the assumption not A, then can you guess what's? Yeah. So then we could prove B without either A, just from gamma itself. So for those of you who know about natural deduction, people sometimes consider this as one of the possible rules that one might have that's equivalent to classical logic. If It's a standard proof principle in classical logic. To show something holds, you might assume something and then assume its negation. There are various proofs in set theory that say if the continuum hypothesis holds, we can prove the result, and also if the continuum hypothesis fails, we can prove the result, for example. And actually, a really famous example of a proof along these lines was oh gosh, what was his name? The guy that worked with Hardy a lot in the
Indian?
No, not Ramanujan. Littlewood, right. So yeah, so Riemann had this formula estimating the density of primes, and his formula was always either underestimating the actual density or overestimating the actual density of primes. And Littlewood proved that actually, even though as far as people knew it was always underestimating, actually it changes sign infinitely often. So although it was underestimating, it actually eventually overestimated and goes back to underestimating and so on. But in order to prove that, he proved it whole. That follows from the Riemann hypothesis, and also it follows from the negation of the Riemann hypothesis. Anyway, that was really that's stuff from more than 100 years ago. Right. Okay. So this is the useful proof principle, and we have it in the Hilbert proof system. So that's the proof system and some meta-theoretic results about it. Part of me feels a bit guilty for not doing these proofs, but they are available online, and it's somehow. They're not the world's most exciting proofs to see in a lecture. Well, I don't think any of the proofs that we're going to have today are going to be the world's most exciting proofs to see in a lecture. But we're coming to a main result, which is the completeness result for the completeness theorem for secret calculus. And I do want to spend as much time as possible on that. So the point is, we're now going to, as I said, this is rather similar to the entailment relation that we had in lecture 2 in idea. It's a different. In lecture 2, the entailment relation was about logical entailment, logical consequence. A is entailed by gamma if A holds in any structure in which gamma holds. So whenever you've got a structure in which gamma holds, then A also holds. And here we've got the kind of proof theoretic version of that. We can derive A from the assumption that the formulas in gamma hold. And the soundness and completeness is that these two are the same thing. So this is theorem, soundness and completeness. And it's basically the following are equivalent. So any set of formulas gamma and formula A, the following are equivalent. Prove A from gamma, and secondly, A is a logical consequence of gamma. And here, implication 1 implies 2 is called soundness. And the implication 2 implies 1 is called completeness. But the idea behind the name soundness is that what we're showing is that the proof rules themselves, the axioms and proof rules themselves are sound in the sense that they don't do anything wrong. They don't, they're sound with respect to what they're intended to do. And the whole point is that of them is that they're supposed to mimic entailment. You know, the idea behind them is we're trying to derive consequences of the formulas in gamma. And they do indeed do that. So soundness basically means we did not include any incorrect rules and axioms in our system. Completeness is, well, indeed, the proof rules and axioms are complete in the sense that if we have if a consequence is true, if an entailment is true, then indeed we can find a proof for that. That's a much deeper result. Soundness is quite easy to prove. You just need to prove that every axiom is valid and every proof rule is indeed, respects entailment, essentially, follows entailment. Whereas completeness is, I think, very intuitively a much more complicated property, because just from the fact that A is a logical consequence from gamma, we need to be able to find that we can actually find a proof of A from assumptions in gamma. So that's a deep result, and this is the first big contribution of Kurt Gödel to logic. So he proved this in his PhD thesis, I think. I think this was 1930. And I already talked in the second lecture about how Kurt Gödel is in this interesting position that he proved a completeness theorem and an incompleteness theorem. And but we talked about that already. So before going on, there is something to clarify here. So actually, I don't think I defined entailment in lecture 2 in such a way that it makes sense in this context. Is there can somebody spot the gap?
Or was it for sentences also?
So I think in lecture 2, I just defined it for sentences. So here, this is for formulas. So the meaning of, so this is, we've been overriding this symbol numerous times. So we now have another meaning for formulas. But it's very similar. So the point of formulas is we've also got free variables in them. So for sentences, we had for all structures, if all, remember, we've defined this to mean all formulas in gamma are true in the structure M, then all formulas then A is also true in the structure M. Now we've got some free variables here, and so we simply quantify over environments for interpreting the free variables, and we stick the environments here. And of course, good. So just for the conoscenti in the audience, people define Hilbert systems in different ways, and sometimes it's defined without any restriction on the generalization rule. And in that case, one gets a different entailment relation here, where you quantify it over all environments here, and then you again quantify over all environments here. That is less natural for giving a completeness proof. and also it relates less well to other proof systems. So I prefer this style of doing it. I mean, that's only for the cognoscenti, as I said. For our purposes, we'll use this notion. Right. So this is really the main theorem today: soundness and completeness. Soundness, you simply prove that every axiom is valid. Hopefully you did that in your head. When I gave the axioms, hopefully you could see that each one of those axioms and every instance of it was a valid formula. And you prove that the inference rules preserve truth, essentially. That's obvious for modus ponens. You have to do a little argument for the generalization, but it's not hard. So once again, I'm going to leave that to, there's an argument there in the handwritten notes. What I want to go to is the proof of completeness, because that is a much deeper result. And this is going to be the main effort now for the rest of the lecture, is going to be how to prove completeness. So it's not obvious how to approach this, because we've got two very different things. We've got quantification over structures for entailment, and if something very set theoretic holds, we need to somehow manufacture a formal proof from that, where a formal proof is something very concrete and syntactic. It's basically a finite list of formulas. So how can we do that? Well, there are ways of giving proofs along those in that direction. They tend to work better when you've got a sequent calculus for doing that style of proof. The easier thing to do in our case is to turn it around and prove the contrapositive. What we're going to show is that so we want to show if the entailment holds, then there is a proof. So the contrapositive we show if there is no proof, then the entailment will fail. And to show an entailment fails, well, we're showing that something universally quantified over structures fails. So we just need to show the entailment fails, we need to manufacture a structure that witnesses this implication fails. So we need to manufacture a counter structure, if you like, that refutes the implication. So this turns out to be a good way of thinking, that we go from the non-existent, we use the fact that there does not exist a proof to manufacture a structure that shows that this implication fails. But in fact, we can make it more explicit, this other way of thinking about it, by reformulating the completeness property to an equivalent property, which is a bit simpler, called model existence. So I introduced the notion in lecture 2, I think, of a consistent theory. And a consistent theory was a theory that didn't contain any sentence and its negation, or in our case, it would be a theory that doesn't contain false, where a theory meant closed under logical entailment. I want to forget that notion of consistency now and have a different notion of consistency, which will be equivalent to it once we've got complete soundness and completeness. And this is the notion of consistency defined by the proof system. So we're going to say a set of formulas. There's not just a set of sentences. We say a set of formulas gamma. So always in this lecture, gamma can be a potentially infinite set of formulas, is consistent if it's not possible to derive falsity from that set of formulas. So if we negate the derivability relation, so if false is not derivable as a consequence of the set of formulas. And actually, the notion of consistency that I defined in lecture 2, we are going to have a need for a name for that, and we're going to call it satisfiable. So we say gamma is satisfiable if there exists a structure that makes all the formulas in gamma true. So if there exists structure M, well, these are formulas, so then they've got free variables. So to make the formulas true, we need to also interpret the free variables. So we ask that there exists a structure, there exists an environment such that the formula is true in the environment. Okay.
Gamma there maybe a set of.
No. Yes. Yeah. Yeah. Thank you. Yeah. And it's an easy consequence of soundness that satisfiable implies consistent. I won't write down the argument for this, but I'll just tell you. So satisfiable implies consistent. Well, let's turn that round and do the contrapositive. And the contrapositive of this is for all structures, for all environments, every formula in gamma is true. Hang on. Sorry, sorry. So contrapositive is for all structures and all environments, every formula in gamma is false. No, hang on. It's not true that every formula.
Well, the negation is what you said just now.
Okay. So where am I? So we want to show not consistent implies not satisfiable. Okay, not consistent is that false is a consequence of gamma. By soundness, we have this entailment. So then, suppose it were satisfiable, there would be some model and some environment in which every formula in gamma were true. By this entailment, then false would also be true in that model and that environment, but of course false is not true in any structure. Okay, so it's basically unwinding the definitions, and I'm sorry I got confused. And the point is that the other implication is equivalent to completeness. We're going to call that the opposite implication. We're going to call that model existence. We're going to prove that the converse is a property we call model existence, and we're going to prove this. The theorem model existence, and model existence says if gamma is consistent, then gamma is satisfiable. In other words, it has a model. And this is the theorem we're going to prove. And I'll just let me just give you the short argument here that once we've proved model existence, we have completeness. So I want to show that proving model existence is enough for completeness, but it's basically, again, pretty much like what I got into difficulty with here, but it is basically a similar kind of just unwinding the definitions argument. So I want to show model existence by its completeness. Something I want to show. So we want to assume model existence, and we want to show completeness. So suppose suppose A is the logical consequence of gamma. And we want to show that we need to show that A is derivable from gamma. So let's suppose not. Suppose A is not derivable from gamma. Well, in that case, gamma together with not A is consistent. Because there's a little argument for this. If it weren't consistent, then we would have that false is derivable from gamma together with not A, in which case, by the deduction theorem, we would have that not A implies false is derivable from gamma, which is the same as not A. But then we had the implication not A implies A as one of our consequences of schematic consequences of the axioms. So by modus ponens, we get that A follows from gamma, and that's the contradiction. Okay. So gamma together with not A is consistent. So by model completeness, gamma is gamma. So then gamma together with not A is satisfiable by model existence. So this says there exists a structure and an environment in which all the formulas in gamma are true and in which not A is true, but that contradicts that gamma entails A, because it says in all the structures and environments in which gamma holds, A holds, not A holds. Okay, so this contradicts that. Okay. So this model existence property gives us completeness and is basically equivalent to completeness. So what we need to do is, the idea is we start off with a set of consistent formulas gamma, and from that we want to build a structure in which all the formulas in gamma are true, showing that it's satisfiable, and that process is enough to give us completeness. And this seems like a natural stopping point, actually, because now we get, this is the thing we're going to prove in the last hour. So the last hour is going to be a technical hour, but the proof, for me, to my mind, this is a nice proof with some nice ideas in it. I'm not going to do every detail because that would be impossible in 1 hour. But there are sufficient details in the accompanying handwritten notes. Are there any questions? Okay, so we'll have the break. It's 3 minutes to on the clock on the back wall, so we start again at 12 minutes past.
So those are some notes that we don't have.
Okay, so the goal of the last part is to give you as much of an outline as we feel like we want to see. Well, maybe at least as much as I want to give of this theorem, the model existence theorem, from which we've seen the completeness theorem follows. And so I'm going to try to start with the high level ideas and then sort of gradually go into the details. And at some point we obviously won't see all the details. The basic idea is we obviously start off with a consistent gamma, and we want to show that gamma is satisfiable. So we want to manufacture some model, some structure out of gamma in which every formula, together with an environment in which every formula of gamma is true in that structure. The main lemma we're going to use for this is called, well, one of the main lemmas is going to be called saturation lemma. This says the following. So if gamma is consistent, we cannot, it's a set of formulas and we can't derive false as a consequence of gamma, then the idea is we extend it to as large a set as we possibly can while maintaining consistency. Okay? Then exists, let's call it, maybe I should check what the notation in the notes is rather than making up my own as go along. Okay, gamma prime. So it exists a superset, gamma prime of gamma, so we throw in as many formulas as we can, maintaining consistency, satisfying, and it's going to satisfy three key properties. So firstly, we've maintained consistency. Secondly, it's as large as possible. And to say that, we say that, the property we really want is that there's no other formula we could throw in that would give us a consistent set, or that either throwing that formula or its negation would give us a consistent set. Actually, it's not that. Sorry, it's kind of, maybe it's the same. So actually, the property we want is this. For every formula A, either A belongs to gamma or its negation belongs to gamma. So this is called, this first property is called consistency, obviously. This is called completeness. So it's like the, remember we had the notion, this is gamma prime, yes, thank you. Yeah. Remember we had the notion of a logical theory being complete in the second lecture. Logical theories are just sets of sentences, but it was basically the same property, but just the sentences in that case. And the point here is that this is actually equivalent to gamma prime being as large as possible, because if we had a formula that neither it nor its negation belonged to gamma prime, and gamma prime's consistent, then by the lemma that I had on the board before, that if both a formula, if you can derive something from a formula and its negation, then you can derive it without. we see that if we've got an A for which neither A nor not A is in gamma prime and gamma prime is consistent, then it's possible to add at least one of them to gamma prime and maintain consistency. So we can always, if we've got a formula, we've got a theory that's consistent, we can, and we have a formula that's neither it nor its negation is there, we can add one of them and maintain consistency. And this makes sure that there are no such formulas left that we could potentially add to get to consistency, to maintain consistency. And the third property is that if we have the negation of a universally quantified property in gamma prime, then for some term t, we have that the negation of A with t substituted for x belongs to the theory, belongs to the set gamma prime. So for some term t, we have that the negation of A with t instead of x belongs to gamma prime. Now the idea here is that by this, we maintain consistency. By this second property, every formula or its negation belongs to the set of sentences. And here, whenever a universal property, the negation of a universal property holds, so the negation of the universal property is like saying there exists an x for which A doesn't hold for x. That's an abstract property talking about existence in, that's an abstract property talking about existence in whatever structure we're thinking about, whatever structure we're talking about. But we have a very concrete way of finding such an element for which A fails. Namely, there is some term that gives us such a thing. And an important consequence of this is that for such gamma prime, if A is a consequence of gamma, if A is derivable from gamma prime, then A belongs to gamma prime. So remember again, in the second lecture, we had the notion of a theory. A theory is closed under entailment. And here we've got much the same thing as a complete theory. We're looking at formulas rather than sentences, but this is the same completeness property. And this is, and instead of closure under entailment, we've got closure under derivability. And this follows by a similar argument to we had before, which is using the completeness property that if A didn't belong to gamma prime, then, well, not A would have to belong to gamma prime. But if not A belonged to gamma prime and gamma prime and A is derivable from gamma prime, then we'd have then actually this theory wouldn't be consistent in the first place. So I won't go into it's a very short argument for this, which I won't go into. So actually, one of the main efforts in the proof is to prove this lemma. So I'll postpone this right until the end. Maybe just to say now that this lemma in generality requires the axiom of choice to prove. But if one assumes that the signature is countable, then it does not require the axiom of choice. Doesn't require any form of the axiom of choice. But let's assume we've proved this for now, and we'll see what we can do with it. And the point is, once we've got this, it's actually now quite easy to find our model. There's the structure we want and the environment. And this is a very nice construction. I mean, this isn't exactly how Gödel proved the results, But this is a modern way of doing things, but you know, Gödel's proof did something similar. But the kind of thing I'm going to do now is a very common device in logic and related areas, also related to things that one does in algebra. We want to construct a structure, and what we're going to do is we're going to construct the structure from using this completed theory to guide the construction, and construct it essentially from syntax of formulas, well, syntax of terms. So let me just check the notes, but just to get the notation. Aha. Yeah. So this is one property. Before. Well, actually, maybe I'll start now. So we're going to define the structure. And the structure is simply going to be, we have a hint here, because whenever a universal quantifier fails, we find some term that gives us a witness to the negation of that property. So the idea is actually we're going to construct a structure in which terms are the elements. And this term here is going to really be the element in the structure that witnesses that the universal quantifier fails to hold. So we define the structure, so curly M because it's a structure, gamma prime because it depends on gamma as follows. And it's simply, only I'm lying a little bit. So gamma, so that the underlying structure is, but it's not quite true, the set of terms. Can anyone see the reason that it's not quite true? And the hint here is that the logical language always contains equality.
Should it terms up to equality?
Yeah, so we need to, so, you know, X and Y are different terms, but gamma prime could perfectly well contain, might perfectly contain the formula X equals Y, for example, in which case they need to be the same. So what we observe is that also for such gamma prime, the relation, let's define a relation on terms to hold if and only if the formula T equals U is contained in the set gamma prime. And this is an equivalence relation. Equivalence relation. It's an equivalence relation because the equivalence relation properties of the equality relation are provable from the axioms. I showed that for the symmetry property. You can also prove reflexivity is obvious, it is an axiom. You can also prove transitivity. So they're provable from the axioms, and then we've got this closure under logical consequence, under closure under derivability here, and that gives us this, that this is an equivalence relation. So the underlying structure is terms modulo this equivalence relation between terms. Yes?
So I think in the book we're kind of using this model.
Which book?
Well, the routing book, but this model has a name. So if you could just remind me what the model is. It Hankin model? Is it Hankin model?
It might be. I mean, there is something called the Hankin model.
Yeah, well, I think this is the in the chapter on logic programming, so I'm not sure.
Yeah, so a Hankin model in logic programming is a kind of smallest model. You maybe don't need to question by equivalence in that case. I'm not sure. Yeah, I forget. Anyway, the general idea here is a syntactic model. People often call such things term models because they're constructed from terms. So here we've just said what the underlying set is. We need to say what the interpretation in the structure M prime of a function symbol f is, and what the interpretation in the structure M prime of a predicate symbol P is. So if we give, so suppose f has arity, they use k in the notes, so let's use k. So if we give it, so the function symbol f, if it expects k arguments and we give it k elements of the structure, that's k equivalent classes of terms as arguments, yes?
M prime, curly M prime is not curly M G prime.
Oh, yeah, it should be gamma prime, yeah. Thank you. Yes, the notes are correct. Okay, any idea what this would be?
I guess the equivalence class of the real.
So the equivalence class of the term f t1 to tk. And then, of course, you have to prove that this is well defined. It doesn't matter which representatives we take here, but it's well defined because of that last axiom, the seventh axiom, which proves that this equivalence relation is a congruence with respect to all the function symbols. So let's not go, there are going to be lots of details we don't verify, and the last details that one would ever want to verify are details about preserving related functions and relations preserving and relation preserving equivalence classes, in my view. Those are always very tedious things. So relation symbol. So, okay, and a suggestion for when the predicate symbol with its k arguments, when will this hold? So this is, so this should hold, this is the property, this is, we define this to be true if and only if.
Well, if it's true for the representatives.
Which means what? What does being true for the representatives mean? So that's, we put P for the representatives. What does being true mean?
Should be this.
It belongs to gamma prime. Okay, that's our measure of truth here. So the idea is that gamma prime, yeah, we've got it by the syntactic construction of making the consistent set as large as possible. But gamma prime is like our set of everything that's true in the model under, yeah. And we're going to get that from this, but we still need to, so this works just out of the tin, but we still need an environment. So our environment, define an environment, rho gamma prime, which interprets free variables which interprets variables, yeah, or free variables in the model. So the environment will interpret the variable x as, any suggestion?
It's equivalence class in the variable x.
Yeah, the equivalence class of the variable x, yeah, indeed. And that's it. That is the structure of the that is the construction of the structure. So there are two things to verify now. We want to verify that we wanted to verify that the original gamma is satisfiable, has this structured environment in which all the formulas are true. So we've defined a structured environment, but we still haven't proved that all the formulas in gamma are true in that structure and environment. So that's one thing to prove, and the other one is the proof of the saturation lemma. So let's do the first one first, because we've got this on the board. Let's rub out the properties So we want to show that all the formulas in gamma are true in this structure under this environment. Okay, we interpret the formulas under this environment and they're true in the structure. So actually the reason we need gamma prime is, well, we couldn't make this definition without it, but also gamma is a subset of gamma prime. So what we can prove more easily is that all the formulas in gamma prime are true. But it's important that we're dealing with, it's important that we prove this for all the formulas in the larger set gamma prime. So the crucial lemma now is this: for all formulas A, it holds that A is true in the structure M gamma prime under the environment rho gamma prime, if and only if A belongs to gamma prime. Okay, so gamma prime is actually the set of all formulas true in the structure. And this is something we prove by induction on the structure, the logical structure of the formula A. So if it's an implication, we're going to get this from the same fact holding for the two component formulas out of which the implications form. If it's a universal quantification, we're going to get this from the corresponding fact for the formula inside the, well, actually, for all the corresponding formula holding for all substitution instances of the formula inside. So it's going to be induction on the logical structure, by which I mean what counts for the logical construction. The logical structure are the connectives and the quantifiers. So if you substitute a term for a variable, you're not changing the logical structure because you've still got the same framework of connectives and quantifiers. So proved by induction on the logical structure, and let's actually consider one of the cases, which is the universal quantifier. So the notes have all cases. Well, one of the nice things, we've got this very restricted language. We only have implication and universal quantification, so they're basically only two cases anyway. We also have the false formula, but that's trivial. So the case that A is a formula of the form for all XB. So we want to show two implications. Let's do right to left first. So if for all XB belongs to gamma prime, we want to show that for all XB is true in M gamma prime. So we need to show that for all XB is true in M gamma prime, which means for all elements of the structure M gamma prime, B is true under the environment. B is true in M gamma prime under the environment rho gamma prime, in which we modify to have X taking the value of T. Okay. This is to prove that for all XB is true in M gamma prime. So consider any T. By the closure of gamma prime under derivability, and by axiom 4, I think,
for the first of the axioms for the universal quantifier in the list of axioms we had at the beginning, we have, so by closure of gamma prime under derivability, that was the first of the lemmas I had here after the saturation lemma. We have that, so for all xb is in gamma prime, so also the formula B with t substituted for x belongs to gamma prime.
So by the assumption, by the induction hypothesis, that means that in the structure M gamma prime, under the environment rho gamma prime, B with t substituted for x is true. But there was a substitution lemma that was at least in the lecture notes, and I think talked about in the exercise classes as well, that relates term substitution to extending the environment for a variable. And that just says, yeah, if this is true, B with t substituted for x, that's the same as interpreting, that's the same thing as saying that the formula B itself is true under the environment rho gamma, where we interpret x as the interpretation of t in the environment rho gamma prime. But because by the definition of rho gamma prime, the interpretation of every term in rho gamma prime is just the equivalence class of the term. So that's which is the same as whoops. It's the same as this. Okay, so this was one implication. The other implication actually has a more interesting twist in it. So let's look at the other implication. If in M gamma prime, rho gamma prime, if it's true that for all x, if for all xb holds, we want to show that the formula for all xb belongs to gamma prime. Suppose not. So then by the completeness of gamma prime, its negation belongs to gamma. The negation of this formula is in gamma prime. So then the negation for all xb is in gamma prime. Did I give a name to the third property in this? I think I forgot to. In the saturation lemma, the third property was that if the negation of a universally quantified formula is there, then the negation of some term instantiation is there. So I forgot to give that a name, and in fact, I've even forgotten the name. So the name there in the notes is witnessing. So by the witnessing property, that's property 3 of the saturation lemma. But we then have the negation of B with t substituted for x belongs to gamma prime for some t.
But then, by the induction hypothesis, or rather, so by consistency, that means that B with T substituted for X does not belong to gamma prime. So by consistency, the consistency in the saturation lemma, B with T substituted for X does not belong to gamma prime. So now by the induction hypothesis for the formula B with T substituted for X, by the induction hypothesis, then if this doesn't belong to gamma prime, then the formula B with T for X is false. So in M gamma prime, under rho gamma prime environment, B T for X is this does not hold. And now once again, this is the same thing, i.e., just as by the reasoning before, this substituted formula, the substituted formula in this environment is the same as interpreting B in the environment rho gamma prime, where we modify, sorry, I mean, the writing was not very neat. It never is. Rho gamma prime, where we modify X to be equal to the equivalent class of T, is exactly the same kind of reasoning we did before. So that formula B does not hold, but this contradicts the assumption here that the university quantified formula holds, because if the university quantified formula holds, then every instance of it needs to hold. So contradicting the assumption. Okay, so that's the essence of that lemma. So the remaining thing is to prove the saturation lemma. And here I'm just going to give a very high-level argument. So as I already said, for a general signature, potentially uncountable set theoretically defined signature, the saturation lemma requires the axiom of choice. Actually, the result it really needs is something called the Boolean prime ideal theorem. Although if I were giving the proof in generality, I would prove it from Zorn's lemma because it's easier to do that. But anyway, I'm not giving the details, but I'll just discuss the case. So this is really very high-level outline proof of the saturation lemma for a countable signature. In the case of a countable signature, there are only countably many formulas. There are only countably many terms, so we get a countable model. There are only countably many formulas. So we can just simply enumerate all formulas. We have countably many formulas. So enumerate them. Also, because we're allowed to start off with an infinite gamma, we also have a slightly silly cause of difficulty, which is the following. Suppose we only had a countable supply of variable symbols in our language, and we've got a countably infinitely many formulas, and every variable symbol is mentioned in one of the formulas. The argument I'm going to give then has a problem because it relies at a certain point on being able to find a new variable that doesn't currently occur in gamma. So actually, we enumerate countably many formulas, including a new stock of countably many new variable symbols, just to make sure we've got countably many variables that are not in gamma. Okay? Countably infinitely many. Countably infinitely many variable symbols. So we just add these new countably many variable symbols. We've still got countably many formulas, so we can still enumerate them all. We now go through the formulas one by one. We've enumerated the formulas. We go through our enumerated list, go through the formulas one by one, and simply do, and it's a very easy process, and for n, the nth formula in the list, we simply perform the following procedure. If gamma, and we define let's assume these are the formulas are enumerated for n greater than or equal to 1. We define gamma 0 to be to be the starting gamma, and then gamma n for n greater than or equal to 1 will define to be either gamma together with the formula an, or gamma together with the formula not an. Depending on, can anyone guess when we add an and when we add not an?
Should it be gamma n minus 1?
It should be. Thank you. Yep. But when do we add an? Yeah, but thank you for that. So what property do we not want to break?
I mean, if it's not inconsistent.
Yeah, exactly. We want to maintain consistency all the time. So this, if it is consistent, and otherwise we add this. And if this is inconsistent, then it's consistent, then this one will be consistent because the gamma n minus 1 is consistent. I've already taken you through that argument in some guise earlier today. So anyway, one of these is guaranteed. They might both be consistent, but one of them is guaranteed to be consistent, and we'll just prefer this one. So this is otherwise. Okay. And this maintains the property so actually sort of come round the final corner and on the home straight and basically sniffing the finish line, and I'm now, well, as I said, we weren't going to, I mean, I'm certainly not giving all the details, but I'm quite feeling in the mood to put on the sprint now and actually get through a little bit more than I was expecting to. So anyway, we're going to get there. So with this definition, we clearly have gamma 0. We're always adding a new formula. They're all proper inclusions, and we obviously define, not obviously, but anyway, we define gamma prime to be equal to the union of the gamma n's. And by construction, we have the consistency. So gamma prime is consistent because, well, because all these are consistent. But why precisely? Well, if it weren't consistent, we would be able to prove false. But if we prove false, in a proof, we can only use finitely many assumptions. So if we could prove false using finitely many assumptions, we would have had to encounter the consistency earlier on, because we can only use. And here we have the seed of a very important property called compactness, which is going to be our starting point next week. The consistence because proofs use finitely many assumptions, and every gamma n is consistent. So consistency is easy. Gamma prime is complete. So for every formula, either it or its negation belongs to it. Well, that's obvious by construction. Every formula was considered in the enumeration. So this is immediate by construction. So the only remaining property to prove is the witnessing property. So the witnessing property so that says, suppose it's not true that for all x a, that this formula belongs to gamma prime. If that's the case, now notice that then there is some n at which I was getting very enthusiastic about the finish line, but of course I've been going on autopilot, and I actually forgot a crucial point. Which is that this is actually a little bit simplistic. So what you need to do is in this case, so yeah, I got over keen because I'd forgotten there was a subtlety, which was actually the reason that at the start I sort of knew better that we weren't going to do all details. There's actually an issue here when, in the case that AN is a universally quantified formula and we add its negation, at that very point, we also add an instance of, so in the case AN is for all XB, we actually add gamma n minus to gamma n minus 1, we add not AN, but we also add not B for some VK substituted for X, where VK is one of these nice new variables that is not present in gamma n minus 1. So every time we add a formula, we can only add finitely many of these new variables, because the formulas can only contain finitely many variables. So each of these gamma approximations has infinitely many of these variables that are still fresh, so to speak, not in use. And so that for a fresh VK. And the reason we can do that is because if we if adding this formula turned out to be inconsistent, then from this formula we would be able to derive false. And that's from a negated formula we could derive false. So by the double negation elimination, that means that we would be able to, once we've added not A n, derive that B contains, we would be able to derive the formula B with VK for X. Because VK is not used anywhere, we could then apply generalization rule and derive for all X B, in other words, AN, and then we see that we've got an inconsistency. So there's a crucial argument here. And then once we've done this, the witnessing property is obvious by construction too. The witnessing property. So the real thing to say here is obvious by the correct construction. And we started with the incorrect construction. Anyway, so today we've gone down to the wire. I hope, I'm sorry there were a few issues today, but I hope I gave you a flavour of what the argument is. And I shall publish the handwritten notes online, and the LaTeX notes just contain the proof system, but none of the proofs. Okay, are there any questions before we go? Good. So I wish you a good week, and back in 101 next week.